The MCT2000 combines the power of a high-speed digitizer, spectrum analyzer, and advanced microprocessor to produce an acoustic pressure spectrum. Different components in the spectrum are analyzed to quantify the fundamental frequency and pressure from the direct field, stable cavitation, and transient cavitation. Specifically, the pressure within the fundamental frequency peak represents the direct field pressure from the sound wave. The harmonics, subharmonics, and ultraharmonics represent the stable cavitation, or the cavities that oscillate in size and dimension. Finally, the broadband white noise in the spectrum represent the transient cavitation, or the cavities that implode and collapse. Let's take a closer look at a typical measurement setup. The MCT2000 was designed with a simple-to-use touchscreen interface. Two measurement modes are available. The first mode, called tap mode, records a data point when the user taps to record. This mode is particularly useful to map the acoustic field in a tank. To do so, the user places the hydrophone in a fixed location and taps the record button to acquire a data point. The user can then move the hydrophone to a second location and tap to record. This is repeated to generate a series of data across a tank. All of the data is then saved locally into the meter. Once the data is acquired, analysis can be done by simply exporting the data through an Ethernet connection. Data can then be downloaded through any web browser. There are several files captured for each measurement, including the data summary file and a spectrum file for each respective data point. These files can be saved in either ASCII or binary format, which can then be easily imported into Microsoft Excel for further analysis. Here you can take a closer look at the tank uniformity and even review the lower level spectral information for a deeper understanding of the cavitation performance. With this approach, high-resolution maps can be generated in various orientations to characterize the tank performance and identify uniformity issues, standing wave effects, and even common failure modes such as debonded transducers.